Her. Okay.
Sorry, we're done.
You're starting. Okay. All right. So now we're eigenvalues and eigenvectors are something that's supposed to be covered in our first linear algebra course, 326, although chances are it isn't really. And then we did come up in some other classes. So what I'm going to do is make sure that at least we have the basics down of these. And at the very end of a course is when I cover how to compute them numerically. But for the time being, it's just enough to know what they are and a few essential properties. And also why I need to introduce them early is for a specific purpose. Suppose I have a sequence of vectors xk. And the way I will define this sequence is, so x0 is something arbitrarily chosen. But to make this even remotely interesting, to choose it to be non-zero anyway. And once you have that, then each subsequent vector is obtained by multiplying by some fixed matrix A. So you just keep multiplying by A over and over again. Okay. Now, this is going to come up in certain contexts. For example, when we try to compute selected eigenvalues and eigenvectors of a matrix, we end up multiplying repeatedly by that matrix. Also, when we study later iterative methods for solving systems of linear equations, as by contrast to the direct methods that you learn in an earlier class, like Gaussian elimination, to study the error, like the error after each new iteration is a previous error multiplied by some matrix. And of course, we want that error to go to 0 as the iteration continues. So the question I'm going to pose for this general sequence is, what property should the matrix A have for the limit of this sequence to be the 0 vector? Wow, this is the most adorable staple I've ever seen. New student and retention program, Southern Miss. Now, using our previous discussion about norms, we can try to get an answer to this question. So the vector itself, xk, converges to the 0 vector if and only if any norm of xk converges to the number 0. But now, that would mean that I can define xk, I can write xk using this formula as a times xk minus 1, which is equal to a squared xk minus 2, and so on. I can apply this repeatedly. And it doesn't matter which norm I'm using. So the manipulations I'm about to make will apply for whatever norms we've covered. So this is the same as a to the k x naught, just by applying this formula for each new vector k times. Now, so we want that to go to 0. But now let's take a look at that last expression, norm of a to the k x naught, using properties of norms. So the norm of xk is equal to the norm of a to the k x naught, and this norm has to be greater than or equal to 0 because it's a norm. But this is less than or equal to norm of a to the k times the norm of x naught. That's the submultiplicative property I'm using here, that the norm of a matrix product is less than or equal to a product of the norms. And then I can use that submultiplicative property repeatedly to, on this, say that I have a norm of A raised to the kth power. So I'm exponentiating a number now instead of a whole matrix times norm of x naught. Okay. So now we have this for an upper bound. And so if this can go to 0 as k goes to infinity, then certainly this is going to go to 0 too. That's the squeeze theorem from calculus 1. But you probably never hear that again. Okay. Now, x naught is some fixed vector you've chosen. So, in order for this expression to go to 0, so this goes to 0 as k goes to infinity if what happens? What do we need to be true to make, so as k keeps increasing, what do we have to have true to make sure that goes to 0? Keep in mind, what are you raising to the kth power? Because you can't do anything about this. That's just what it is. But to make the whole thing go to 0.
A is a matrix.
Yeah, but now we're taking norm of A. Norm of A is just a number. And that's what you're raising to the kth power. Yeah, so we need to have to be, if it's strictly less than 1. So this is true if the norm of A, whatever norm we have, infinity norm, 2 norm, 1 norm, if some norm is less than 1, then that will definitely cause the norm of A to the k to go to 0, because it's bounded by it. So, however, that condition, while it is sufficient to make xk go to 0, but not necessary. What I mean by that is, it is possible that there's some matrix A where if you take any norm, any of the p norms or Frobenius norm, that those norms turn out to be greater than or equal to 1, but the sequence that's defined this way is still going to go to 0. So what we'd like to arrive at is a necessary and sufficient condition for the sequence of vectors to converge to 0. Okay, so that's why I'm going to talk about eigenvalues and eigenvectors. So, in other words, instead of an if, we want an if and only if situation. Okay. Actually, have any of you not dealt with eigenvalues in a class? Seen them somewhere? Okay, yeah, because it's not even necessarily in algebra. Like you saw them in PDEs, they came up there. So, okay, yeah. They're just so useful that way. Okay. Now, assume that A is an n by n matrix, so this A has to be square. So if you have this equation satisfied, vector equation, A times x equals lambda times x. X has to be a non-zero vector. And lambda is some real or complex number. Doesn't matter, it could be 0 or non-zero, doesn't matter. But if this equation holds, then lambda is called an eigenvalue of A, and x is an eigenvector. Okay. Now, if I take this equation and rearrange it, so I just put everything on the one side. So ax minus lambda x is 0. But now I go ahead and factor out an x on the right side. And I get a minus lambda I identity times x is the 0 vector. And this came up before we were talking about determinants, because x, because here we have a situation where we're multiplying a matrix by a vector, we're getting 0. X is non-zero. Therefore, the matrix A minus lambda times the identity is singular. In other words, it is not invertible. I recently gave those several equivalent conditions that if a determined matrix is non-zero, then the matrix is invertible. Ax equal b is a unique solution. Ax is 0 if and only if x is 0 and so forth. So now we have the opposite situation. So what we can say is the determinant of A minus lambda times the identity is 0. So this is an equation that characterizes the eigenvalues. So in your first linear algebra course, what's happening is you learn about eigenvalues the first time, you learn about this, and then they give you simple matrices, 2 by 2, 3 by 3, whatever, and you set up this equation and solve it and compute eigenvalues that way. Now, and what's interesting is when you write out determinant of A minus lambda times identity, it's a polynomial. Okay. So if A is n by n. Thank you. Yeah, my brain is extra fried this week, so.
That deserves a point. And you could have just totally screwed up the whole class and the whole lecture. I mean, that was a big life-saving moment there. And let me tell you how frustrating it is when you forget to move the computer.
Yes, I can hear you yelling at your TV even from miles away and months past. I am so sorry. I owe you so many gummy worms for that. Okay. Anyhow. So this expression, determinant of A minus lambda times identity, is the polynomial that has degree n, and it is called the characteristic polynomial. And so this is a thing that wouldn't come up in like a PDE class. You're finding eigenvalues, but in that case, you're taking the equation that's equivalent to ax equals lambda x and solving it directly. here, that in matrix land, that equation leads to this one. So the eigenvalues, they are polynomial roots. Okay. So n by n matrix, you're finding the roots of a polynomial degree n. That's why in homework problems or first linear algebra course, if they ever get to eigenvalues, the matrices involved are pretty small. Otherwise, you'd have to try to find the roots numerically. So this means that there are n eigenvalues, although they may repeat, just like roots of a polynomial can repeat. Also, even if a matrix is real, the eigenvalues could be complex, because a polynomial with real coefficients can still have complex roots, but they have to be complex conjugates of one another. Now, before I get into other properties of eigenvalues, the funny thing here is when a student first learns about eigenvalues in a linear algebra course, and they learn about this, and they're accustomed to forming a characteristic polynomial, finding roots by some way, using factoring techniques or whatever. So you think, okay, one computes eigenvalues by finding polynomial roots. But in MATLAB, it's the opposite. Because first of all, that's a hopeless exercise if a matrix is large. And polynomial roots, they're not it's a numerically unstable problem. There are certain polynomials you can construct, there are famous examples, where even if you know what the root should be, so I'll do my little MATLAB interlude here. There are two functions in MATLAB or Octave that are inverses of each other. So P is equal to poly of R, and R is equal to roots of P. And R is a vector that represents the roots of a polynomial. And P is a row vector, whereas R would be a column vector coming out of this. It could be a row or column vector going into poly. It's a row vector of coefficients of a polynomial. So, as an example, R could be the vector containing values 2 and 3. So P would be the coefficients of a polynomial x minus 2 times x minus 3, but all FOILed out. So it would be x squared. So it would be that. So x squared minus 5x. So x squared minus 5x plus 6. All right. Now, so what these functions do is here you feed poly the roots, and it gives you the coefficients, assuming a leading coefficient is 1. If you have a coefficient, you feed them to roots and then function, and then it'll compute the roots for you. And so ideally, you should have, if you take a vector R and you feed it to poly to get coefficients, when you take those coefficients and you feed them directly into R, you should get the same thing back. But as you'll see when we get into the next section, which I might get to today or certainly Thursday, about computer arithmetic, floating point arithmetic, that there's error involved. And for certain polynomials, this could be way off. So I'll give you an example. Look at this example. If you set R equal to the vector 1 to 20, so polynomial degree 20 that has roots 1 through 20, the integers, and you feed this in, the R that comes back out is not going to agree very well. And if you take this to an extreme, like maybe 1 to 50, you'll find that even though you have 50 real roots, some of the roots you get back are complex. It's that bad. And this is using what's normally a very stable, numerically stable method of finding roots. So what happens is, instead of if you're trying to find eigenvalues, MATLAB does not find eigenvalues by computing polynomial roots by some other method, but it does find polynomial roots by computing eigenvalues. Because what it does is, this function roots constructs a matrix whose characteristic polynomial is the polynomial you want for roots of. And then it computes the eigenvalues of that matrix by standard methods for computing eigenvalues, which I'm going to cover at the very end of the semester. So this is an example of how the way you learn to solve these problems in math courses, especially for small-scale problems, is totally different than how it's done in real applications. Okay, so after I cover floating point arithmetic very soon, and then eigenvalue methods at the end of the semester, you'll see have a better feel for why this kind of behavior occurs. Okay. But yeah, I was finding it quite interesting that the way it's done is a complete flip of how students learn to do it the first time. Okay, so here's some properties of eigenvalues and eigenvectors that will come up from time to time. So if lambda is an eigenvalue of A, and I'm going to introduce a shorthand for this because I don't feel like writing that much. In other words, I say lambda is an element of this set, lambda of A, and we refer to this set as a spectrum of A. That's the set of all eigenvalues at most n that A has. So you'll see often the spectrum or spectral, that word being used in association of eigenvalues. Okay, so if lambda is an eigenvalue, then your matrix A has at least one linearly independent eigenvector. And I say linearly independent because any multiple of an eigenvector is also an eigenvector, as long as the multiple is non-zero. Because if you have ax is equal to lambda times x, and I multiply both sides by a constant c, then I can move the c around because it's just a scaling constant. So I can say a times cx is equal to lambda also times cx. So x is an eigenvector, cx is an eigenvector. But there's always one particular direction, like a unit vector, that serves as an eigenvector. Now, there could be more than one. It's possible that a given eigenvalue has more than one linearly independent eigenvector associated with it. So the eigenvalue is like a repeated root of the characteristic polynomial. That can happen. Okay. So that's first property. I've got a number of them. Second property is if you have this kind of relationship, B is equal to PA P inverse, where so the matrix P has to be invertible, because I'm just using the inverse, then the eigenvalues of A are the same as the eigenvalues of B. So they have the same spectra. And we say that matrices A and B are similar. That's the term we use to describe that situation. Also, the term we use is P inverse AP is called a similarity transformation of A. Now that's going to be crucial for when we try to compute eigenvalues later on, because what we do is, starting from our original matrix A, we keep performing similarity transformations of it in order to reduce A to a matrix of a simpler form for which we can easily obtain the eigenvalues. Now, I haven't said yet what kind of matrix is easy to find the eigenvalues of, but that's coming on my long list of properties. And that's how any of the problems we're talking about this semester go. We try to reduce the original problem to a certain category problem for which the solution is easy. Yeah, stuff like that. Well, if in a case where A is symmetric, yes, that's exactly what we do.
And if it's not symmetric?
Well, it's on my list of properties anyway, but triangular would be enough. But yeah, a matrix that is triangular and symmetric is diagonal. Okay. Speaking of symmetry, that's my next property. A is symmetric. Actually, I should say real and symmetric. So in other words, A equals A transpose. And the other scenarios is complex and Hermitian. So really the most general statement I can make is A is equal to its Hermitian transpose, so transpose and complex conjugate. So real symmetric or complex Hermitian, and complex Hermitian would cover this case. Then the eigenvalues are real numbers, so they will have no imaginary part. So the because I'll be covering how we find eigenvalues for a general matrix and then specializing to the symmetric case too. And a lot of simplifications happen in a symmetric case, and one of them is the fact that you know you have real eigenvalues. Okay. By contrast, if A is real and it's skew symmetric, or if it is complex and then we say skew Hermitian. So in this case, A equals minus A transpose, or Hermitian transpose. Then any eigenvalue of A either has to be 0 or it has to be purely imaginary. So I times some real number A. Okay, so in other words, for real parts, so another way of putting it is the real part of lambda, which is abbreviated RE for real part, and then there's IM for imaginary part, it has to be 0. So no real part here, no imaginary part here. Okay. Next, if A is a real matrix and lambda is an eigenvalue of A, then and I'll make it a complex number, u plus iv. Then lambda conjugate, so the bar refers to complex conjugate, which is u minus iv, is also an eigenvalue. And that's something that you would expect because eigenvalues are polynomial roots. If you have a polynomial of real coefficients and you take the roots, then what you get are real roots, or you get complex roots that must occur in complex conjugate pairs. So that's where that comes from. Okay. Now, a few more properties. Almost forgot again. Okay, so next property is A is, and I use shorthand from before because I want to get used to it, lower triangular or upper triangular. So A is a triangular matrix. Then the set of all eigenvalues of A is just equal to the diagonal entries. Okay. So that's what we want to do, is a method for computing all the eigenvalues of A. We try to perform similarity transformations of A to reduce A to triangular form. Doesn't matter whether it's lower or upper, we just happen to choose upper. And then we can just read the eigenvalues off the diagonal. And that comes from the fact that the determinant of a triangular matrix is a product of all the diagonal entries. So it's related to that. Okay. And speaking of the determinant of A is equal to the product of all the eigenvalues of A, including any repeats. Like if you have lambda being a multiple root, so if it appears as a root k times, it has to occur k times in this sum. Right. So the determinant is the product of all the eigenvalues. Now I use this notation, lambda I of A, to indicate this is the first eigenvalue of A, second eigenvalue, third eigenvalue, all the way up to n. Okay. And then the last property, TR of A, which is the abbreviation for a trace of A. So something that's very easy to compute. It is the sum of all of the diagonal entries of the matrix, but it happens to coincide with the sum of all the eigenvalues. So in fact, for a 2 by 2 matrix, you can compute the determinant very easily. You get the product, and then you compute the trace very easily. You get the sum. So you know the sum and product of the two eigenvalues. And from those two conditions, you can figure out what the eigenvalues themselves are. And it boils down to using a quadratic formula, but still. So at least you know something about the eigenvalues, how they relate to one another, even if the eigenvalues themselves might not be easy to compute. So another way of putting this is, since it's equal to the sum of all diagonal entries, if I perform a similarity transformation of A, the eigenvalues don't change. And though the diagonal entries will change, their sum is not going to. So in other words, this is a way of saying the trace of A is equal to the trace of any similarity transformation of A. Okay, you should notice that, and I was supposed to think when I did this. Here I wrote PA, P inverse. Over here is P inverse AP. Both for similarity transformations. The point is, the matrix on this side is the inverse of this one. So this is a different similarity transformation than this, assuming the matrix P is the same in both cases, but they are still similarity transformations.
Well, you wrote it both ways over there. I thought that was intentional.
Oh, that wasn't actually.
So do you, I mean, does it matter? As far as like...
Not really. No, the only thing that matters is that the two matrices on either side of A are inverses. Yeah. So, but for sake of notes, and presentation considerations, I should have done that. So. Oh. Okay, so you're just hoarding points. You know what?
Hopefully we won't even need them, but you never know.
Well, someone keeping track of them? Because I'm sure not.
I totally am, Peter. She has two. She has one. I have one. Does he have one? Did I give you one the other day? No. Okay.
Did I give you one? Did I give you one?
I'm working for the members.
Okay.
Okay, so you just never get out of teacher mode.
Never.
Never.
Unfortunately.
All right.
So don't forget to change your notes,
Okay. Let's see. I have about half an hour to see where I'm at in the notes. Okay, so I did that. Covered that. Oh, okay.
You know, I've written P inverse, and then I looked up there, and you wrote it the other way, so I went and erased it, and now you just wrote it the...
Okay. I'm trying to gauge whether I have time to prove that. It's not in the notes, but it's not always fun to stick with the notes entirely.
Never. Be incredible.
Okay. All right. I'm gonna give this a shot because this is impromptu, but I've done this before. It's just been a long time. So what I would do, and this is good practice using certain basic formulas.
What is this? What are we doing?
I'm going to prove that.
Okay.
Okay. So I want to prove that the sum of AII is equal to the sum of the diagonal entries of P inverse AP. And so for that, I need to use a formula for matrix multiplication to write out what the diagonal entries are. So, okay. So what I'm going to do is I have to apply it twice because I have three matrices altogether. So that's the same as saying like sum k equals 1 to n of P inverse IK times AP KI. And then I have to apply that matrix multiplication formula again to the product AP. So that's going to give me, so I have three sums. And that will give me P inverse IK, I'll use a capital letter. I normally wouldn't, but it'll stand out better. AKJ PJI. Okay. So now at least I have some expression, and I'm going to make this capital as well, because they are the same thing. All right. So now I have something involving the entries of A on both sides of the equation. So I need to show AII is equal to, and I'm going to rearrange this because all right. Okay, I need to have the sum over K and J out front, and I have A, KJ here. So this is interesting because here I have the diagonal entries. Here I'm going to have all the entries. And then I have the last sum over I. And what I have is P inverse IK, and then PJI. But in fact, it's going to be more convenient to write this differently. In fact, this proof is almost done. Alright, so if I write it the other way, it's easier to see what's going on. PJI, P inverse IK. Here, we have this common index, I. We can use a matrix multiplication formula again. So this is what entry of what matrix product?
Like they're inverses of each other.
That's good. That's going to be important, yes.
I know.
Okay. So this whole thing is equal to what?
Well, it's definitely JK.
Yes.
The
P inverse JK.
Yeah.
But PP inverse is, yes, it's identity. So this is equal to Kronecker product JK. It's equal to 0 unless J is equal to K, in which case it's equal to 1. So therefore, all the terms in this sum go away, except for the ones where K is equal to J. So I get J equals 1 to N, J, the sum of the diagonal entries. So, done.
Jeez.
Alright, so it's nice to know I can still do proofs off the top of my head. Okay. Let's see. Already covered that. Alright, so now I can return to the reason why I wanted to talk about eigenvalues in the first place, about sequences of vectors, where you're multiplying repeatedly by A. Okay. Let's see, 25x. So if the absolute value, or in the case lambda is complex, a complex modulus of each eigenvalue is 1 for all eigenvalues of A, then then that sequence, so this expression, which is actually going to write this way, which is the xk that I defined earlier, converges to the 0 vector. And turns out the converse is true. That a to the k times the starting vector x naught goes, if this is true, for any vector x naught, and I'm just using complex to be as general as possible, then all the eigenvalues must have an absolute value strictly less than 1. Okay. Now, a more convenient way to describe this is this expression, rho of A, so that's the Greek letter rho. That is the maximum over all eigenvalues of A of the absolute value. So this is the maximum absolute value you can get among all the eigenvalues of A. So So what we can say using this definition is the spectral radius of A is less than 1 if and only if this sequence of vectors, a to the k times x, goes to 0 for all vectors x that you could choose. So this is our necessary sufficient condition that I was wanting earlier. So you get a situation where a matrix may have a norm, or any norm, greater than or equal to 1, but the spectral radius could be less than 1. And that will be enough to drive the sequence of vectors to 0. Okay. And speaking of norms, there is a nice relationship between the spectral radius and any natural norm. So well, not A. So in other words, what we mean by that is norm of A is defined to be the supremum of norm of AX divided by norm of X for all non-zero X. So any norm that falls into that category. So in other words, the Frobenius norm is not part of this because it's not induced by any vector norm. So I can say that let's suppose that the spectral radius of A is equal to the absolute value of some eigenvalue lambda. So lambda is the largest eigenvalue. And let's suppose that X is the corresponding eigenvector. So what that would mean is the norm of lambda X, which is equal to the spectral radius of A times X, because I can pull this lambda out as long as I take the absolute value, but that's equal to the spectral radius. But this is equal to the norm of AX, because AX and lambda X are the same. But now I use the submultiplicative property. This is less or equal to the norm of A times the norm of X. So now, if I compare this equation, or this expression, with this expression, and the left one is less than or equal to the right one, X is not 0. So I can cancel the norm of X on both sides, and I get the spectral radius is always less than or equal to any induced norm of A. Now, so I should mention, I said a Frobenius norm is not part of this because it's induced. But the Frobenius norm of A is always greater than or equal to the 2 norm. And the 2 norm is part of this. So a spectral radius is less than or equal to a Frobenius norm also. Okay. So that's the relationship between spectral radius and norms. But we also have, if A is symmetric, we have an equality. The spectral radius of A is equal to the 2 norm of A. And in the general case, and gave this position before, I just wrote it differently. The spectral radius of A is equal to the square root, no, that's not right. 2 norm of A is equal to the spectral radius of A transpose A, and then take the square root. Okay. And if A is symmetric, A transpose equals A, you just get A squared in here. And when you square a matrix, you're squaring the eigenvalues. So that's worth mentioning on its own. The spectral radius of a to the kth power is equal to the spectral radius of a, that number raised to the kth power. So that relationship applies to eigenvalues, and the similar relationship applies to the spectral radius. Okay. All right. So now I can state some equivalent conditions related to the spectral radius and convergence of certain sequences of interest. So here's some equivalent conditions. So if one of them is true, they're all true. So spectral radius of A is less than 1. We can also say that the limit of the norm of A to the K is 0 for any natural norm. Also, we can say that as K goes to infinity, the ij entry of A to the K is 0. So any individual entry is also going to 0. So this is true for all ij from 1 to n. And finally, for any vector x, the limit of A to the K times x is the 0 vector. All right, so this will come in handy when we're studying convergences of sequences of vectors, especially for the analyze convergence of iterative methods. That the knowledge of the spectral radius will help. Okay. All right, so any questions about that? All right, I have one last item. Hopefully I can do it in the 15 minutes that are left. Okay. So something else we could use norms for. So the question we're going to tackle is if matrix A changes by a small amount. If we quantify the size of a change in A, can we also quantify the size of a change in the inverse? So norms can help us get an answer to that. Okay. Now, suppose that, we work with a generic P norm here. Suppose we have some matrix F, and we know that in some norm, what was it, 1 norm, 2 norm, infinity norm, is less than 1. Well, that would mean that the spectral radius of F is less than 1. And therefore, we can also say that, based on the conditions I wrote earlier, we keep raising P, raising F to a power, and let the power go to infinity. We're going to get the 0 matrix. So, what that means is, if I look at this expression, I take a sum of powers of F, starting from 0 up to K. But then I let the upper limit K go to infinity. this is a partial sum of an infinite series. And I can then multiply this by identity minus f. So now what I can do is I can move this in here. Now, okay. This is a telescoping, I created a telescoping series because if I move this in here and then distribute, I get all the terms canceling out, except for identity minus f to the k plus 1. And then I take the limit of that as k goes to infinity. But that's going to 0. So what's left is identity. So now what that means is, what do I have here? This expression in parentheses is a matrix, and that's a matrix. The two matrices multiply together to give you identity. Therefore, how do they relate to one another?
They're inverse.
They're inverses of each other. So I can say that identity minus f inverse is equal to the, now we know it's convergent. Check my notation here. Yeah. I'm still using I. I equals 0 to infinity of f to the I. So now we have an expression for the inverse of this that we can use. Okay, and the thing is, identity minus f, we know that it's non-singular because of this condition, that its norm is strictly less than 1. Because to get an idea as to why, that the norm of f times x is less or equal to the norm of f times the norm of x, but that is strictly less than 1. Okay, so and that would mean that by a reverse triangle inequality, that would be greater than or equal to wait. Yeah.
Right.
Yes. Okay. All right. And so what happens here is, but also these two can't be equal. One's strictly less than the other. This whole expression must be positive. So in other words, the norm of this vector, therefore, cannot be 0. So if you have, this is assuming that x is non-zero itself. So the only way to get I minus f times the vector equals 0 is if x is 0. That means I minus f is non-singular. Right? So that's basically a quick proof that it is. So it stems from this, but the norm is less than 1. Okay. Now, yeah.
You got, so in the last inequality,
Yeah.
you have the norm of f and vector x minus the norm of the vector.
Yeah.
And then when you factored out, or like when on the other side of the inequality, you put I minus f. Like is that,
Well.
is that on purpose or?
Oh, okay. Okay. Well, it's supposed to f minus I.
Right.
Yeah. Signs don't matter in this because we're taking norms.
Because it's only absolute value.
Yeah. So really what I proved was f minus I is non-singular.
Right, but.
Okay. But yeah, that's
I just didn't want to assume that.
Yeah. Okay, let's see if I can get through the rest of this. All right. So what we have is so identity minus f inverse raised to p power using properties of norms, including triangle inequality. That's what I'm using right here. And also the submultiplicative property. So I use a triangle inequality to be able to pull out the sum from the norm, and then the submultiplicative property to pull the exponent out of the norm too. And this is less than 1. This is a convergent geometric series. So this whole expression is equal to 1 over 1 minus norm of f, or p norm of f. Okay, so at least we have a bound on the norm of identity minus f inverse. So now, all right. So let's suppose I take a matrix A and I perturb it by E. And it's a small perturbation, so that if I define R to be the norm of A inverse E, P norm, is less than 1. So as long as I choose the entries of E to be small enough, close to the zeros I need, I can make sure that this happens. So I'm going to let my matrix F be minus A inverse E. So what that would mean is A plus E, which is the same as A minus A inverse E. No. Not what I wanted. Okay, so if F is A minus A inverse E, that means that AF is equal to minus E. So this is the same as A minus AF, which is the same as A times I minus F. So it gives me a way of expressing a perturbed matrix in terms of F. So now because A is non-singular, and I minus F is non-singular, the product is non-singular. So it means that as long as the perturbation of A is small enough, the perturbed matrix will also be non-singular. But what I really care about in 5 minutes is what can I say about the norm of the difference. So I can look at the norm of A plus E inverse minus the norm of A inverse. Now, okay. So that's going to be the same as, all right, so A plus E is same as A times I minus F. So I can write this as the inverse. The inverse of a product is the product of the inverses in reverse order. So I can have I minus F inverse A inverse minus A inverse. Okay. All right. So that seems a little bit simpler than what I had in my notes. Actually, not really like what I have in my own notes at all. Okay, so then what I can do is, all right. Of course, I want to make sure it turns out to be the same. Okay. God, I hate when I do this. It's been years since I looked at these notes. Yeah, 'cause somehow there's two A inverses in here. That's going to drive me batty. But, okay. Because what I could do is factor an A inverse out of a product. Okay. Okay, this is really going to piss me off. Okay, well, A inverse E, that's F. So, okay. Okay. I see. That's a really convoluted way to do it, but okay. So instead of going down that path, what I'm going to do is, so I'll write inverse minus, and what I'll do is I'll throw in I minus F inverse, A inverse, and A times, now this is equal to A plus E inverse. So now I have A plus E inverse that I can factor out to the right of everything. So what's left is I, from over here, minus I minus F, that's factored out, times A plus E inverse. And then what I can do is I can simplify what's inside here. I minus F, that cancels, and what's left is F. And then F is the same as minus A inverse E, A plus E inverse. And then I can put A plus E inverse as how I meant to write it the first time. That's the same as I minus F inverse A inverse. And now we have two A inverses going here. So now what I could do is, norm of a product is less than or equal to a product of the norms. So this is less than or equal to norm of A inverse squared, norm of E, and then we have the norm of I minus F inverse. But I have that over here. That's less than or equal to, these are P norms, 1 minus R, where R is equal to the P norm of F. So this result was used, dang it. All right, someone's going to yell at me over that. Well, two people actually. Yeah. Oh, wow.
Why do you substitute R, like,
Oh,
for ease of writing, but you
yeah.
put it off to the side anyways? I mean,
Because it was in my notes that way. Okay.
I mean, is that how we're gonna see it? It looks like that with
Yes.
R representing.
Yes.
Okay.
Yeah, and we're already making the assumption that we chose E so that the norm of F is less than 1.
Right.
So we're not dividing by 0. So now we have a handle on, based on how the inverse, how the original matrix changes, which is the norm of E is the size of your change in A. This is an upper bound on how much the inverse can change. So if norm of E is small, this can still be small, but how small? Well, that depends. First of all, it depends on how close this norm is to 1. Also, what about the norm of A inverse? That could be particularly large. So unfortunately, we can't rule out that a small change in the inverse may still lead to a large change in the inverse, but at least we have a handle on how bad it could possibly be. Okay, so there you have it. And I'm pretty sure I'm past time. Oh, only 3 minutes. Okay. I know. Okay, we're good. But at least we're.
Could you prove it the other way that you started?
That's a real good question. Well, I mean, I'll keep this recording. Also, I feel bad for people watching, but I had this cut off for much of the time, so I got to be more careful about that.
They can pause it.
Yeah. So, well, yeah, they can see it now, but I'd like them to be able to see the thought process. So, they can see the thought process when I try to do this the other way, and see if that can be salvaged. Because I thought that was a much more intuitive first step. I mean, I got these notes a long time ago from what Gene Gall did in class, and trying to put all that together. So, and then basically transcribing what he did. But that was way back in 2003. So, so you don't have to stay.
No, I want to say it.
Okay, but you can if you want. All right. Well, so A, because I'm using that factorization anyway. So A plus E is the same as I minus F inverse A inverse minus A inverse. And the thing is, over there, an A inverse eventually got factored out anyway. So inverse minus identity A inverse. So in other words, now I have to show that all of this is equal to what I'm going to circle right here. That. Okay. And yes, what's in square brackets there must equal what's circled over there. And what I could do, for instance, is, and the thing is, minus A inverse E, that is equal to F. Okay, I think I know how I can do this. So what I'm going to do is, if I express I as I minus F times I minus F inverse, and then I still have the A inverse outside the square brackets. Yep, I think it's going to work. Okay. And now I will factor out an I minus F inverse to the right. So that'll leave me an identity here minus I minus F, I minus F inverse, A inverse. So I have the two pieces, and I minus F, that's just going to be F. And then F is minus A inverse E. Okay, so yes, it all worked out. So, and a proof that did not get cut off by the camera. Yeah, I like that one better. So, yeah.
Wait, is it? That, relationship between, so I minus F inverse times A inverse is A plus E?
Yeah, I have,
Yeah,
oh, I erased it.
it was in that, here, sure.
Yeah, where did that come,
Yeah.
where did it go? Okay,
Yeah,
I was looking down, I was trying to like do it on
yeah.
the, A plus E inverse. Well, yeah.
Yeah, because
No, I get that part. I'm just trying to find it in the next step. Okay, I'll just write more steps on my paper because you skipped some, I think.
well, okay, so
No, I'm way down there.
here to
Okay,
here.
I get that. And so then that part is A plus E inverse, right? Yeah.
Oh, but well, this is, but I didn't use that
Oh, would you?
because this stayed here, but
Oh,
this
you
simplified.
that.
Yeah.
Yeah.
Oh.
Okay.
We used it in the last one, that's why I was just we would use
Yeah.
it.
So the only place where I use it. Oh, yeah. Here I used it. Yeah, I used it in both proofs, but at different places.
Right,
Here I used it immediately,
yes,
and here not until.
Third to last line?
yeah.
Yeah, right here.
Yeah.
I'm right
Okay. Cool.
Right.
Right away. Okay.